Hello, my name is Joheb. I am one of the discussion board team leads for week 9. This week's problem goes over errors in the RSA encryption algorithm. Now, in this discussion board, we will kind of be going over some of the human errors we might make, or what happens if we choose different values for things that we should be picking, and how or why it causes the algorithm to fail. So to start off, our values that we need to encrypt and decrypt are P1, P2, and P3. That's 10, 18, and 27. Our prime values, P and Q, are given as 23 and 29. These are our default values. And then we use these two values to calculate N and B. To calculate N, we simply take P times Q, which gives us 667. And for B, we do P minus 1 times Q minus 1. That gives us 616. So for the first question, we're looking at what happens if we choose a value for E that is not relatively prime to B, which is 616. We're going to try to encrypt and decrypt all the values with this value of E. And we're going to see what issue we see and try to give us some ideas about why that happens. So first, let's think about what it means to pick a value of E that's not relatively prime to B. Relatively prime means if we do the GCD of E comma B, if that's equal to 1, then that would mean E is relatively prime to B. So we need to pick a value for E such that the GCD of E comma B is not equal to 1. So in this case, we select a value for E that's equal to 4. And then you can see if we do the GCD of 4 comma 616, we get a value of 4. So this means right here that E is not relatively prime to B. So we go ahead and calculate our C values, which are the encrypted values for P1, P2, and P3. And the numbers we get is 662, 257, and 509. We simply use the formula P1 to the power of E mod mod N to be able to calculate our encrypted values. So then when we try to calculate when we try to decrypt this, the first value we're going to need is D, and that's something we get from ED is equal to 1 mod B. And when we try to do that, for this case, what we actually get is an undefined value. We cannot calculate D, which also means decrypting this is actually impossible. Now, why is this? The equation to calculate D, ED is equal to 1 mod B, that actually derives from the fact that E is relatively prime to B. So from GCD of E comma B is equal to 1, that's where it's actually derived from. So since this is not equal to 1, this inverse does not work. And that's why D is not possible to calculate. And this is why the algorithm will not work if we choose a value for E that's not relatively prime to B. So the next question, suppose we let Q is equal to 23, thereby having non-distinct primes. Encrypt and decrypt all the values. What issue do you notice, and any idea why this happens? So for this case, we're simply selecting the same values for both of our primes, P and Q, which is 23. So if we try to go ahead and encrypt and decrypt, we get the encrypted values as 9, 509, 311. And if we go further and try to decrypt these values, we go ahead and calculate our D first. And in this case, since E is the original, or E is selected as a value that is relatively prime to the B value that we calculate from the given Q, Q and P, we are able to calculate D, unlike the first question. But the issue we see is when we go ahead and try to decrypt this, the p-values or the original plain text of values that we get out of this is not the same as what we started with. We get 286, 64, and 96. If we go back 2 slides, we'll notice our P1 is 10, 18, and 27. And that is not the same as what we get over here. So the decryption does not produce the same plain text values as the original values, which means the algorithm is simply not working. And this is because when P is equal to Q, it simply does not allow the decryption algorithm to become an inverse function of the encryption function. And this is why we get invalid results, which means if you have P is equal to Q, the RSA algorithm will not work. For the next question, suppose we calculate D by mistakenly finding it using ED is equal to 1 mod N instead of mod B. What issue do you notice? Any idea why this happens? So let's go ahead and try that. We let E is equal to 5, which is actually relatively prime to B. And if we go ahead and calculate our encrypted values, we get C1, C2, C3 as 617, 624, and 403. Then when we start to decrypt, we calculate our D value using ED is equal to 1 mod N. That's given in the question, so that's why we use 667 instead of 616, which is our B value. So we actually use our N value to calculate D. We do get a result for this, but when we try to use this D value in P is equal to C1 to the power of D mod N, we get invalid results for our plain text value. So we get 166, 188, and 3. Again, if we go back to our first slide, we see that P is actually supposed to be 10, 18, and 27, and that's not the case here. So it's not 10, it's not 18, not 27. We actually get incorrect results. We actually get incorrect results for all 3 plain text values. And the reasoning for this is it kind of goes back to the explanation for the first question, where ED is equal to 1 mod B is actually derived from the fact that E is relatively prime to B. So GCD of E comma B is equal to 1. So when we're doing ED is equal to 1 mod N instead of mod B to calculate D, this is not a valid inverse function for GCD of E comma D is equal to 1. And that's why the value that we're calculating for D is actually something completely different and not related to what we're trying to do in this algorithm. And this is why, since D is not the inverse exponent of E, we end up getting incorrect values for our plain text results when we try to decrypt this.
Hello everyone, my name is Esperanza and I'll be going over questions 4 and 5. For question 4, we are asked to choose prime factors such that n is smaller than our largest value to encrypt, which in our case is 27. If we choose prime factors p and q to equal 2 and 11, then our n will equal 22, which is smaller than 27. Our b would then equal 1 times 10, which is just 10. We can also let e be relatively prime to b, and so we can set it to 5. We can now encrypt our plaintext values, and we get C1 equals 10, C2 equals 10, and C3 equals 1. If we attempt decrypting our C values, we run into an error since we cannot compute the decryption exponent, and therefore decryption is not possible. As we can see, our n needs to be larger than the largest plaintext value, since this will ensure a proper execution of the modulo operation in the encryption and decryption equations. For question number 5, we have a simplistic encryption algorithm where C equals f of p equals 4 minus 2p. And suppose we make a mistake and write p equals f inverse of c equals c over negative 2 minus 4. First, we must identify the issue, then perform the encryption and decryption process on our three plaintext values. Clearly, our initial mistake would be deriving the p function incorrectly. Our p function should equal c minus 4 over negative 2. The encryption gives us the values c1 equals negative 16, c2 equals negative 32, and c3 equals negative 50. We can then decrypt back to p1 equals 4, p2 equals 12, and p3 equals 21. Our p-values do not match up with our original plaintext values as expected. The critical issue that occurs in this problem and the others has to do with not following the algorithm correctly. In other words, if we change any part of the RSA encryption and decryption process that does not follow the rules, we will not be able to correctly decrypt back to our original plaintext values, since the decryption would not be the exact inverse of our encryption.